Okay, in this video I'm going to show you another way that you can actually come up with the rate law. Last week we discovered that if you have data, the concentration, the molarity of certain reactants, and you have the rate at which they're appearing or disappearing, that you can come up with a rate law just by comparing two experiments that have similar molarities and two that have different molarities. Okay? And you can come up with a rate law by comparing it with the rate. However, if you have something that does not show you the rate, let's say you have the concentration of A over a certain period of time, but you don't have the rate. Well, one thing you can do is you can graph the concentration of A versus time. And let's say you do that. Let's say we take these numbers right here and we graph it versus time. You might get something that looks like this. Okay? All right. Well, that's not very linear. So that's not really telling a lot, so it's not really helping us that much. So there's one thing you can do. You can make two other graphs. If you graph A versus time, which was what I just showed you, then also graph the natural log of A, the concentration of A versus time, and also graph 1 over the concentration of A versus time, the reciprocal. Okay? So you're gonna make these three graphs here. Only one of them is going to be linear. Okay? Now right now, if you'll notice, this one is the only one that's linear. But this one could be linear. This one also could be linear. But only one of them will be linear. If this one right here is linear, which it's not, that means that this reactant is to the zero order. And your rate law would be rate equals K, concentration of A to the zero order. Okay. If this one is most linear, which it is, then it's to the first order. So if the natural log versus time graph is most linear, then it's to the first order, and the rate order would be, or the rate law would be rate equals K, concentration of A to the first. If this one is most linear, which it's not, it would be to the second order. Okay? So it'd be rate equals K to the concentration of A to the second. Okay? So one of these three graphs is going to be most linear. Whichever one is, wins. If this one is the most linear, then it's to the zero order. If this one's most linear, it's to the second order. If this one is most linear, which it is, then it's to the first order. Okay. If this one right here is most linear, well then we have an equation that can represent the line. And it's kind of like a y equals mx plus b. The y being the concentration of A, okay? The x being time, the B being the original concentration. And so therefore the M would be the slope of this line, and that slope of that line would be our K, which is our rate constant. This down here tells you how to find the half-life. If this one is most linear, then I have a y equals mx plus b equation for that slope. And my y is the natural log of A. My my x is still time. My b right here is just the natural log of my original amount. And then once again, the slope, m, right here, is going to equal my k value, which is my rate constant. Finally, and also here's the half-life. Half-life is 0.693 divided by k. Finally, if it's the last one, and this is a straight line, then I'm going to have a y equals mx plus b that looks like this. This would be my y, 1 over a. This would be my x, time, plus this would be my b, which is the original, 1 over the original amount. Okay, and once again, this would be a positive slope, so therefore it wouldn't be negative k, it would just be k, my rate constant. And the half-life for second order would be 1 over k times a original. Okay, so once again, half-life, you probably heard of half-life last year through nuclear chemistry. Half-life is the time it takes for something to decay in half. So if I have a certain molarity here, like 8 molar, then what is the time it takes to get to 4 molar? Okay, here's 8 molar, here's 4 molar, here's the time that it takes to get there, 24 minutes. So the half-life for this is 24 minutes. Every 24 minutes it decays in